Welcome. In this video, we'll walk you through the workflow of optimizing a marine propeller using ALTAIR Inspire. We'll focus on the workflow to perform structural analysis, along with topology optimization. Let's dive right in. To begin, we import the 3D CAD model of the marine propeller into ALTAIR Inspire. Let's first look at its key measurements. The blade diameter is 410 mm, providing the necessary thrust for marine applications. Now, let's talk about the material. This propeller is made from aluminum 6061 T6, which chosen for its excellent material properties. With the model ready, we now simulate the forces acting on the marine propeller during operation. Torsional load, a torque of 120,000 Nm is applied at the hub. This force represents the rotational energy transferred from the engine to the propeller, driving its motion and creating thrust. Aerodynamic forces, at the blade tips, lift forces of 200 N act upward, generating the thrust needed for propulsion, while drag forces of 50 N resist the motion. These forces mimic the airflow interaction typically experienced by rotating blades. Hydrodynamic pressure, a distributed pressure of 2 Nm² is applied across the blade surfaces to simulate the resistance from water. This pressure ensures that the propeller's design can handle the drag forces generated in marine environments. Centrifugal forces, due to rotation at high speeds, radial forces peak at 500 N near the blade tips. These forces pull outward from the hub and test the propeller's structural integrity under rotational stress. With all forces and constraints defined, we proceed to structural analysis. Several load cases were defined. The analysis focuses on stress distribution, deformation patterns, and safety factors. High-stress zones, like the hub, are carefully reviewed, while deformation is kept within acceptable limits. These insights guide the optimization process for a lighter and stronger design. To begin the optimization process, first, we define the design space. Now loads. Torque, 120,000 Nm. Aerodynamic forces, 200 N lift and 50 N drag. Centrifugal forces, radial forces peaking at 500 N. Hydrodynamic pressure, 2 Nm². We have applied the same loads and constraints from the structural analysis. Additionally, shape controls like split drawing and symmetry were applied as constraints during optimization. Once the design space and loads are set, we define the optimization constraints. Objective: maximize stiffness and reduce material usage by targeting 30% of the original mass. The optimization results reveal an efficient and lightweight propeller design by strategically removing material while maintaining structural performance. The design focuses on key stress paths and load-bearing regions, ensuring it can withstand operational forces effectively. The optimized design is then evaluated for manufacturability by fitting it into poly-NURBS. Thank you for watching the video.